Test selection is not a creative decision. It follows almost mechanically from 4 questions about your data. Work through them in order, and you'll arrive at the correct test almost every time. Question 1 is the most important and the one most often skipped. What type is your outcome? Continuous, like weight, temperature, or milk yield? Binary, yes or no, like disease present or absent? A count, how many events per animal? Or time to an event? Each outcome type has its own family of tests, and using the wrong family is a fundamental error that invalidates everything that follows. Question 2 determines the scale of comparison. 1 group versus a reference, 2 groups, 3 or more. This separates t-test territory from ANOVA territory. Question 3 catches the most consequential error. Are your measurements from different animals independent, or are you measuring the same animal more than once? Repeated measures on the same animal violate the independence assumption of standard tests. Always use the paired version when the design is paired. Question 4 is about assumptions. For parametric tests, the key assumption is approximate normality. Violated in a small sample? Use the non-parametric alternative. Continuous outcomes, 2 parallel families of tests exist: parametric and non-parametric. Parametric tests are more powerful when their assumptions hold. Non-parametric alternatives rank the data rather than using raw values, making no assumptions about distribution shape. The choice comes down to sample size and normality. With more than 30 observations per group, the central limit theorem generally protects you. Proceed parametrically. With small samples and clearly skewed data, use the non-parametric alternative. A practical point about equal variance. The standard student's t-test assumes both groups have equal variance. Most modern software now defaults to Welch's t-test, which doesn't make that assumption. If your software gives you a choice, always use Welch's. It costs you almost nothing in power and protects against a violated assumption. For more than 3 groups, you're in ANOVA territory. For predicting a continuous outcome from 1 or more predictors, linear regression, covered in Talk D, and when you have a baseline covariate measured before treatment that you want to control for, ANOVA, covered in Talk C. Binary outcomes with 2 groups, chi-square is your starting point, but with a non-negotiable assumption. Every expected cell count must be at least 5, not observed count, expected count. Calculate it as row total times column total divided by grand total. If any expected cell falls below 5, use Fisher's exact test. Fisher's exact test works for any cell size and produces equivalent results when chi-squared would have been valid anyway. McNemar's test handles paired binary data, the same animal assessed before and after, or matched case control pairs. Standard chi-square on paired binary data is wrong. It ignores the correlation between the paired observations. When you have a binary outcome and multiple predictors, chi-square can no longer help you. You need logistic regression, which adjusts for all predictors simultaneously. Logistic regression is covered in Talk D. Count and rate outcomes need Poisson regression. The key distinction from binary, a cow can have 0 mastitis events or 1 or 5. That's not a binary outcome, it's a count. And when animals have unequal observation periods, include an offset to convert counts into rates per unit time. This is covered in Talk E. Assumptions checking determines whether your test produces a valid result. The software will give you an answer regardless. It's your job to verify the answer is trustworthy. Normality, plot a histogram. Approximately bell-shaped? Good. With more than 30 observations per group, the central limit theorem generally protects you regardless. For small samples with obvious skewness, use the non-parametric alternative. Shapiro-Wilk gives you a formal small sample test, but visualizing the histogram is often more informative. Equal variance, run Levine's test. Significant result means variances clearly differ between groups. Switch to Welch's t-test. Most modern software defaults to Welch's now, so check your output to confirm. Independence is the most consequential violated assumption and the one that can't be fixed after the fact. It's not something you test statistically. You determine it from study design. If your animals come from multiple herds, they share environment, management, and disease history. They're not independent. If you measure the same animal twice, those observations are correlated. Either situation requires paired tests for simple designs or mixed models for complex ones, covered in Talk E. Reference table is your practical tool. Before opening statistical software, work through the 4 questions and find your row in this table. A few scenarios worth pausing on: the lameness score before and after Farrier in the same cows, paired t-test, not independent. Before and after measurements on the same animals must be analyzed as pair. Using an independent t-test here throws away the power advantage of the paired design. Predicting metritis from multiple predictors, binary outcome, multiple predictors. That lands in logistic regression, not chi-square. The moment you want to estimate the independent effect of each predictor while holding the others constant, you need a multivariable model. In mastitis events per cow year across 3 housing systems, the outcome is a rate, not a binary event, and not a normally distributed continuous measurement. Poisson regression with an offset for unequal observation periods, covered in Talk E. The tip at the bottom is genuinely the most important advice on the slide. Draw your data first. A histogram before a t-test, a scatter plot before a regression, a box plot to check outliers and spread. A good plot frequently tells you which test is appropriate before you've done a single calculation, and it often reveals problems that statistical tests alone would miss. Decision tree captures the entire talk in one visual. Keep it as your reference. Every analysis starts with outcome type, then moves through group number, paired or independent, and assumptions. The most consequential error on this decision tree is at the very first branch, choosing the wrong family for your outcome type. Linear regression on binary outcomes. Chi-square on continuous outcomes. These aren't minor statistical errors. They produce fundamentally wrong answers with false precision. The draw your data tip closes the loop. Statistics confirm what good visualizations suggest. If your histogram looks approximately normal, a parametric test is probably appropriate. If your scatter plot curves, a linear model is probably wrong. If your box plot shows dramatic outliers, non-parametric methods will be more robust. Visualize first, test second, always. Pause the video and work through the scenario using the 4-question framework. This is an applied application of everything in Talk 1. We'll then work through the answers together. Scenario 1, one sample t-test. One group compared to a known reference value, 80 micrograms per liter. Continuous outcome. Key assumption, check normality with a histogram or Shapiro-Wilk test. N equals 15 is small, so normality matters. If clearly non-normal, use Wilcoxon signed rank test against the reference value. Scenario 2, chi-square test or Fisher's exact. 2 independent groups. Binary outcome, yes or no. Check calculate expected cell counts. row total times column total divided by grand total for each of the 4 cells. At sample sizes of 80 per group with rates of 12% and 26%, expected counts will all exceed 5, so chi-square is appropriate. If any count were below 5, switch to Fisher's exact. Scenario 3. Wilcoxon-signed rank test. Same horses measured under both conditions. Paired design. Lameness score is ordinal and clearly non-normal. The paired t-test requires normally distributed differences and should not be used with clearly non-normal ordinal data, and n equals 12. Wilcoxon-signed rank is the non-parametric paired alternative. Scenario 4, one-way ANOVA. 4 groups, continuous outcome. Levine's test is non-significant, p equals 0.41, equal variance assumption holds. Proceed with one-way ANOVA. If the f-test is significant, a post hoc test, Tukey's HSD, identifies which diet pairs differ. Key assumption remaining to verify. Normality within each group. Histogram or Shapiro-Wilk per diet group. Scenario 5. Logistic regression. Binary outcome. Mastitis, yes or no. Multiple predictors simultaneously. Chi-square cannot adjust for multiple covariates at once. Logistic regression estimates the adjusted odds ratio for each risk factor while holding the others constant. Key assumption, check events per variable. You need at least 10 mastitis cases per predictor. With 240 cows and typical first lactation mastitis rates of 15 to 25%, that's 36 to 60 events for 4 predictors. EPV of 9 to 15, borderline to adequate. Scenario 6, McNemar's test. Same 180 cows, accessed before and after, paired binary outcome. Standard chi-square treats the observations as independent, which is wrong here. McNemar's looks specifically at the discordant pairs, cows who change status, non-pregnant before, pregnant after, or vice versa, which is where the information about the protocol's effect lies.